video. All right. Oh, hi everyone. I'm Peter, here to show you what my research is about. So it's a sub-4-nanowatt voltage reference device. Just as a side note, this same thing was published and presented in a recent IEEE conference. Okay, that out of the way. The most important things first. Why are we doing this research? Okay, so electronics, we've got three demands. Wants things that don't take up that much power and still take up small space and still work reliably. So cell phones can last longer. Devices themselves can be more accurate. Now, one of the things to make one of these three things possible, all of these things possible, is a fundamental device called a voltage reference. And what a voltage reference is, it's just a device where you put in a supply voltage and you get an output, where after a certain point it doesn't change even if you change the temperature or change the supply voltage. So now, a device that gives you an output voltage that doesn't change, how is that even useful? Okay, one of the major uses for it are in analog to digital conversion. These zeros and ones, they just depend on how constant this reference voltage maintains itself over different conditions. So that's what a voltage reference is and how it's useful. Now, fundamentally, the voltage reference is as what we see in this picture here. So modern CMOS voltage references are designed like this. There's a current source being fed into a diode-connected load, and for a condition where the output doesn't change with temperature, they design the transistor according to that condition. All right, so that's the fundamental premise. So let's see what other people have done. Okay. So these are just recent designs that have been published so far. So this design from 2007, it shows a current source. So this whole structure here, that's the thing that generates the current, and it's going to the diode-connected load as we see here. So it follows that same fundamental premise. Again, in 2009, there's a variation of a current source, and it's being fed into some other variant of the diode-connected load. Again, in 2012, you've got a current source here. So this is a native transistor where the threshold voltage is 0 volts. So even when you've got nothing here, you've got a saturated current flowing through, and that's how this design treats as a current source. All that is fed into, again, a diode-connected load. So that's how recent designs have been done. They're all following this fundamental premise, and they all share some of the same problems. Okay, so what are the problems of current designs? Well, one major problem are process variations. Everyone designs for some output that doesn't change with temperature. So this condition here implies a 0 parts per million per Kelvin performance of the voltage reference. However, when microchips actually get made, there are these processor variations that make it less than ideal. So one chip could be 7 parts per million per Kelvin, another one could be worse at 45 parts per million per Kelvin. Okay, so the problem is basically inconsistent performance once the microchips get made. Another problem that's common to all these designs is that they all use the standard textbook equations. So weak inversion and strong inversion are accurately characterized as per these textbook equations. But what happens when in moderate inversion, that basically is an unknown in most standard textbooks that describe how MOSFETs work. Okay, so how do we solve these problems in the research? Okay, so with the process variations, we're going to do something called post-fabrication trimming. So it's just some way to adjust that the circuit after the circuit has been made. One example of this is from Dr. Rossi's publication in 2011. Here, what he's done is he's varied the current going into that diode-connected load. So if you had more than enough current going into the diode-connected load, you tend to get an output that goes up with temperature. And if you have less than enough current, you get an output that goes down in temperature. So from here, it's intuitively obvious that somewhere between too much and too little current, there should be just the right amount of current that gives you the ideal output that doesn't change with temperature. So that's basically what the trimming does. You're adjusting something to make the output ideal, even if there are some random process variations. Okay, and as for those inherent inaccuracies, what we're going to do is we're going to ditch that standard model from the textbook and use an alternative one called an advanced compact MOSFET model. This particular model can basically handle all regions of operation, so even moderate inversion, it can handle that pretty well. What that is, you'll see soon in the next slide. So that takes care of what others have done, what the problems are, and how we're going to solve the problems. So before I can even get into design, I have to first of all tell you about the theory that the design is based on. Okay. So what is the advanced compact MOSFET model? Okay, so it's just a model that describes the current in terms of a forward current subtracted by some reverse current, and it's characterized by the equation here. Here we've got this is the current, this is the size ratio, so the width-length ratio of the gate. What we got here, that's the sheet-specific current, so we've got stuff like the slope factor, the carrier mobility, offsite capacitance, thermal voltage, things that generally aren't controlled directly in the design. What we've got here, these are just unitless numbers. So this is the forward inversion coefficient and the reverse inversion coefficient. And how that works is we just put those numbers right into this function here, and that function is related to the terminals of the transistor. So right here we got the gate, the threshold, the source, the drain. So basically this set of equations tell us the current flowing through the transistor and the voltages at the transistor terminals. Now, a common mode of operation for MOSFETs is saturation. So in the ACM model, saturation is described as when the majority of the current flows in the forward direction and not in the reverse direction. And so in that case, IF is a lot larger than IR, and you've got this expression here. Okay, so now in saturation, this IF is the thing that differentiates between the different levels of inversion level. Okay, so with this ACM model, all regions of inversion, they're all it's all a matter of what the value of IF is. So it's just one set of equations for all inversion levels. Okay, so that's basically the ACM model in brief. How does this ACM model relate to this the voltage reference? Okay. So what we've got, if we relate this to the picture, what we see here is the source is nothing, and the gate is the reference voltage output. So just simplifying that and putting it here, you get this. We want an output that doesn't change with temperature. So first of all, some things have to be redefined in terms of how they change with temperature, and then we can make this condition possible. So now we can redefine, to redefine them in terms of how they change with temperature, we do it like this. So the threshold voltage is basically a maximum threshold voltage at the minimum temperature, subtracted by some expected drop in the threshold voltage. So with this expression, we can predict pretty much what the threshold voltage is at any given voltage, any given temperature, sorry. Okay, what we've got here, and we can do the same thing for the thermal voltage, okay, and define them in terms of temperature. So let's take all these messy things and put them back into this expression here, and we get this. So now, the idea is to get this, we have to somehow get rid of every temperature-dependent term in this expression. And the way to do that is just make your reference voltage the same as the threshold voltage at 0 Kelvin. And then from there, we can see that all these temperature-dependent terms cancel out, and all this boils down to these three expressions here. So the idea is, if this condition is satisfied, we get an output that doesn't change with temperature. It's not that easy though, because there's process variations involved. So you make different microchips, you'll have different expected drop in the threshold voltage values. And so if that's different, this expression may not always be true. So you may not always get this ideal output. And what can we do about that? To account for that, what we can do is, you see that IF is related to KBT. So we have to somehow be able to adjust IF. And to adjust IF, the thing we can do is say we keep I the same and change the size ratio, or keep the size ratio the same and change I. Okay, and so that's the idea. Now, that idea is implemented by these structures here. Okay, so for instance, how it works is this shift register, it would activate certain trimming transistors. And say, for example, this particular trimming transistor is not activated, so the current would flow through the load as it normally would. However, if this trimming transistor is activated, then that current just gets diverted away from the load. And so when you've got current diverted away from part of the load, that part of the load is trimmed off, or pretty much is more or less effectively doesn't exist. So that's our way of changing the size ratio using these trimming transistors. And here, what we've got is, if say we don't activate this particular trimming transistor, you'd have less current going through the load. And if you did activate that transistor, you got more current through the load. So that's how we change the current going into that load. Okay, so that's the underlying theory behind this whole thing. That's the foundations of this, of the design involved in this research. So, so now, once we get into design, the first thing that has to be done is the current source. So everything here depends on some kind of circuit that generates current. Okay, so what is that circuit? Well, this is that circuit here. Okay, so this structure here is the current source we need for the voltage reference. And what it is there's a PMOS mirror on the top, and on the bottom we've got an NMOS pair and weak inversion, and feeding some voltage into a load configuration here in moderate inversion. And the premise behind that is this weak inversion pair, it puts some constant voltage at this point here. And say this constant voltage is low enough, then it would force this N4 to operate in trial region of operation. And so MOSFET in trial is more or less like a resistor electrically. And so pretty much a voltage over some sort of effective resistance, that's what generates the current. So the design of this is you have to assume every single branch has identical current. And from that assumption, we can use the ACM model to relate the size ratios and the inversion levels of all these transistors. Also, what needs to be done in design is, because this part of the circuit and this part of the circuit share the same part of the same connection point, then basically the design involving this part has to relate to the design involving that part. And so with all these relationships, and if these conditions are met, the current source can be designed for. Okay, so now, once it's been designed for, then the way to use the current source for any other part of the load is just connect another PMOS transistor to the PMOS mirror, and that's how the current source is used for this particular circuit. Okay, the current source itself might have a problem though. The problem is, if the supply voltage, this VDD, if it goes up, there's a good chance that this current goes up significantly, and that's not what we want. Ideally, the current source is just something completely independent of the power supply. So the way to solve that problem is to have a cascode circuit, and that increases that output resistance. Okay, so for instance, having an NMOS cascode here, we can improve the performance. And the design consideration is just to say the gate voltage has to be more than the saturated drain source voltage here and here. And if that condition is met, we've got better performance and no extra power needed. So, which is a win-win. Now, to make that output resistance go up even more, we can also use a PMOS cascode. So it's the same idea as that NMOS cascode, where you basically have transistors below the PMOS cascode transistors. And it looks like this. Okay? Now, the design revolves around these three transistors. Okay? And so the consideration is similar to that NMOS cascode, where the gate voltage has to exceed that saturated drain source voltage of these transistors here. And if we do that, and also this particular circuit, this is the thing that biases the voltage, the gate voltage for these cascode transistors. So the design basically has to account for the saturated drain source voltage of the PMOS mirror transistor. Now, if these conditions are met, then basically we've got even higher, even more improved performance, more supply voltage independence, and there's only just a minimal extra power needed. That extra power being this one extra branch of current that's needed to make it all work. So that is a current source in a nutshell. Okay, in a very, very brief way, that's how the current source was designed. So what's next? Okay, with the design handled, then we can look at the voltage reference. This is actually a tricky part to explain. So how exactly do we design something like this? Okay, so we know that we have to somehow change the inversion level to account for random process variations. But the question is, how much do we change it by? What's the smallest possible change of inversion level that we need? Okay, And this smallest possible change of inversion level, that's the thing that, that we rely on to determine the minimum current flowing through this whole structure. It's the thing that we rely on to size these trimming transistors and also to size these particular architectures. So the way we decide on the number for delta IF is to see how it changes the performance. So if we change IF by a certain amount, how much does the performance change? And we have to make sure that this change is not too large. Okay, so now the logical answer of how this is designed for follows this whole complete set of equations that are a bit too complicated to explain in a few minutes. Okay, the general idea is if you change delta IF by a certain amount, you have to ensure that the corresponding change of performance doesn't change by too much, so that you don't miss the particular window performance. So this is the logical explanation, but I'm going to ditch the logical explanation. I'm not going to do that. A more intuitive explanation will be done by pictures. So I'll show you what's going on in people's mind when they go through these equations. Okay? So for instance, let's say delta IF, the smallest change of inversion level, corresponds to a change that represents 2 times the desired performance. And say we wanted a performance of 5 parts per million per Kelvin. Okay? And hypothetically, let's say that the output of the voltage reference is at this point here. So it's at a level that's something not really perfect. It's not a straight line. It's not a smooth horizontal line. It's like it increases with temperature. So so we have to activate one of these trimming transistors to fix this. So now, if we activate a trimming transistor and it changes by 2 times the desired level, what we get is we can guarantee that the performance is well within this desired range of operation. Okay, and just to show the idea a bit further, say you activate another trimming transistor, add another bit to it, it will exceed that desirable range, and basically that's not what we're looking for. Now, the question is why 2 times? Why not 3 times, 4 times, 5 times for that matter? Okay? So say hypothetically, changing the smallest possible change represents 3 times the desired level of performance, and say we start at the same point we had earlier. Okay? What happens if it was 3 times? Well, this is what happens. It completely bypasses that desirable window of operation. So basically, if we had too high of a number for the delta IF, the circuit theoretically will never reach its desirable range of operation. So 2 times is good, anything more is not good. That's pretty much the bottom line for the design of the voltage reference. Basically decide what number should delta IF be, and then everything else can be designed accordingly. So that is the voltage reference in a nutshell. And now the design summary is as follows. So the current source, all those 4 branches of the current source, we use 2.1 nanoamps in total. Okay, and these particular architectures, they use up to 1.6 nanoamps. So the whole circuit uses less than 4 nanoamps of current. The design performance we're going for is 5 parts per million per Kelvin. So not an arbitrary number. We chose this based on what is comparable to published works. And also the levels of inversion are from 37 to 59. So basically, if all these trimming transistors are turned off, then we'd have an inversion level of 37. And if all the trimming transistors are turned on, we have an inversion level of 59. And this 37 to 59, what it means is it solely operates in the moderate level of inversion. So this particular design could not have been done by those standard textbook equations. So that's the voltage reference design. Okay. So the next question is, how was it made? Okay, we didn't stop at the design, we actually made the microchip. Let's see now. Okay, so this is what the chip looks like. Okay, so the result of this work turned into this chip. Zoom in a bit closer to the middle, we get a picture that looks like this. So we've got an NMOS, PMOS, shift register, everything needed for this whole thing to work. And how that was made was through software. So the layout software, say we zoom in on the NMOS section, in software it looked like this. And zoom in a bit closer to the section of the NMOS portion, we get a very symmetrical layouts design of the transistors. And now, this symmetry isn't done randomly. It was done on purpose. And the reason is the fabrication involves very, very high temperature, like over 1,000 degrees. So any material subject to this high temperature is bound to have certain sections that go up in temperature faster than others. So for example, let's say this part of the circuit goes up in temperature faster than, say, this part of the circuit. So we've got a hot spot here and a cold spot here. Now, as a result of symmetry, the effects of the process variations because of these hot spots and cold spots, they balance out. Like one example would be this N4 transistor. Part of it is in a hot spot. Another part of it is in the cold spot. So in a hot spot, the transistor would diffuse more, and in the cold spot, the transistor would diffuse less. So now, if they are combined as one, then the idea is by having this symmetrical layout, all these process variations are balanced out. So that's how it was made. Okay. And now, how was it tested? Okay. We couldn't just put a meter to the output of the voltage reference and expect an output. There's a really distinct possibility that this current just flows through the meter and not into the load, and then you don't have an output. So to test that, we got to isolate that output using a CMOS op-amp right here. So with this configuration, the current would flow through the load as normal, and it would output a voltage, and whatever is on the plus would be duplicated on the minus, and then from there we can measure the voltage reference output. Once we're able to measure the voltage reference output, what do we do with that? Okay. What we can do is we turn on all the bits for maximum inversion level, and then once we turn on all the bits, change the temperature. So the expected performance is it goes up in temperature if we turn on all the bits. Also, we do the same thing, but turn off all the bits. So like we turn off this trimming transistor, the next one, all the way up to MSB, and then change the temperature. And then from there, the expected output is that it goes down in temperature. And from there, based on these slopes, we can find a specific point where it neither goes up nor goes down, and that's our ideal output. Okay, then this is the, and then from there we can adjust the bits so that we get a certain voltage, and that certain voltage we then change the temperature, test it again, and that's how we verify the voltage reference chip. So that's the testing method. So the next logical question is, how does it work, right? How well did this whole thing work? The first instinct that we have when we receive the microchip is power it on and see what happens. If it doesn't blow up, it's great. Okay. Ideally, we want something like this. Okay. If your supply voltage goes up, you would expect the output to go up to a certain point and then not go up after it reaches a certain voltage. Experimentally, we get this. So first of all, these are the simulated extremes. So the worst the worst case scenario, like based on process variation, this is the maximum possible output and this is the minimum. And the measured values are well within the maximum and minimum. So what we can see is the measured value, it corresponds very, very closely to what we ideally expect. Okay, so it's not exactly no change. There is like a 2.79 millivolts of change from like 0.9 volts to 3 volts. So that's very comparable performance to some very recently published works. Also, this whole thing works in less than 1 volt. So as I said before, the circuit uses less than 4 nanoamps, and it works in less than 1 volt. So the power consumption of this whole thing, based on this result, is less than 4 nanowatts. Okay, so now we can move on to the next phase of testing. Let's say we fix the supply voltage at a certain point, it's like say 1.5 volts, and change the temperature. What happens? Okay. Ideally, we want a straight line, something that neither increases nor decreases the temperature. Experimentally, we get 3 lines. So what they are is, if we activated all the bits, we got the maximum inversion level, and we get the expected increase in output with the temperature. If we turn off all the bits, then we get that expected decrease. So somewhere between the maximum and minimum, there's got to be some point that neither goes up nor goes down, and that point is shown here. Okay, and so from this scale, it looks like more or less identical to what we ideally expect. Using a microscope, zoom in a little closer, we get something like this. So 1 millivolts of difference, less than 1 millivolts of difference over 100 degrees. The particular performance of this chip is actually comparable with some of the best published works that has been published recently. So that's how that worked. And as I was getting to, how does this particular circuit compare with others? Okay, so in blue, when we got here, this is this circuit, and everything else here, these are recently published works that are voltage references. So in terms of power, performance, and area used is comparable to many of the published works. Another thing I should mention is the temperature coefficient. Okay, so we've only got 4 samples considered here, and so 4 samples, any statistical analysis is meaningless. So we actually went a little further and found the probability in which the performance would fall within this range, and that probability is 93%. But with that out of the way, another thing is we designed for 5 parts per millimeter per Kelvin, but at best we got 8.1. So there's a difference. Okay, why is that? The reason why is second order effects, or at least we think the reason why. And basically, any approximations we made during the design, that could come into play and account for these differences. Also, compared to this design in 2012, it's actually superior to everyone's work in terms of power consumption and the area used. So the question is, why should we even bother considering this work when this one is so much better? There is a catch, okay? This particular design needs transistors that work with different threshold voltages. And first of all, that process is not, those process options aren't available to everyone. And also, the last time I checked, when I looked for the prices of like say, similar process options as this guy, it was like 3 times the price of whatever I was using, which basically is just a standard plain, no special option technology. So basically the strength of this work is, even though it's not better than this guy's, it's a standard alternative. Anyone with the baseline ability to make microchips can use the idea and make a nanowatt chip that works comparably well. So that's the how this circuit compares with others. Okay. Now, what can I say after all that's said and done? Okay, we went all the way. Okay, the design, the fabrication, the testing, everything was working. So I'd call that a success. Okay, these architectures, okay, their performance is, they're more or less identical. So the idea of just changing the inversion level to change the performance of the output actually is experimentally verified in this work. Also, one thing we found out that probably was not well-known knowledge before was there's a large range of inversion level needed to get the ideal output. And for instance, say these are 2 test chips, okay? One chip needed an inversion level close to the maximum. The other chip needed an inversion level close to the minimum. So that implies that IF, the range of that, is actually a large range. And from this equation here, it can be shown that if IF is a large range, the range of the change of the threshold voltage with respect to temperature actually is not just one number, but a range of numbers. This is news because most designs that are published, they assume this to be one number, and let's say the technology data sheets, they just give us a single number for this parameter. But we found here that it may actually be a range of numbers, not a single number. So this may be useful information for any person designing this kind of circuit in the future. All right, so now what can we do to make this research better? Okay. Well, in the design, we can account for those second order effects. So those approximations we made, we could actually, if we counted for them better, maybe we can get the output that's matching closer to our calculations. And so that's something that can improve. Another thing is, to make this chip more useful, we could have some memory cell that saves the whatever trimming transistors have been activated. Right now, if we activate certain transistors and we turn off the power, turn it on again, then you've got to activate the transistors again manually. And so this is just something that can improve the circuit. And also, what I think is important, at least, is to use this voltage reference circuit into a more, implement it into a more useful circuit. So if we use it for actual analog to digital converters or voltage regulators, then the advantages of using less power and still having good performance, that can be realized and basically be a benefit to somebody somewhere. So thanks a lot. First of all, I got to acknowledge 2 parties here. I got acknowledged NSERC for some funding, and the Canadian Microelectronics Corporation for fabricating the chip. So feel free to ask me about anything I presented so far. Thanks.